Okay, now we will look at the first worksheet for industrial automation. So the first topic of today is EP1. EP stands for electro-pneumatics. Electro means electrical, pneumatic means compressed air. So I'm sure everybody know what is automation about, which is aimed to reduce human involvement in performing a task so that you require less manpower to achieve an outcome. So in our context of industrial automation, we are looking at electrical, mechanical, computer-based systems to control the automatic manufacturing of goods. Okay, so in a typical automation process, there's always a control chain. So this is the control chain, and it's made of 4 components: input, signal processing, final, and output. So for input elements, we are looking at replacement of the human sensors. Okay, so it can be push button, electrical switch, limit switch, and even electric sensors. We will touch on this topic on input elements later on in EP3. Okay. Next, we'll look at signal processing element. Signal processing element is looking at the replacement for human brains. Okay, so commonly used will be computers, microcontrollers, and in our context, we will teach you PLC later on. PLC stands for Programmable Logic Controller. Next, we'll look at final control element. Final control element is actually used as a signal conversion to match the signal processing element and the output element. Some of the examples will be directional control valve or electrical contactors. Well, you may ask me, what is directional control valve? Okay, we will touch on this topic later on in EP2, so you just take it as a component for now. And next, we will look at output elements. So output elements is looking at replacement of the human muscles. Okay, so what are these replacement components? Okay, it can be cylinders, okay, or motors. In our daily life, we can see many automated processes. So let me just give you an example using our leaf control system. So in our leaf control system, there are also 4 components of the control chain. Okay, so they have the input, signal processing, final, and the output. Okay, how does the leaf know that which level it has to go or when to open its doors? So for a typical leaf control system, it has a push button, okay, or many push buttons, limit switch, and electric sensors. So for instance, I want to go to level 1 from level 4, I will press the push button. So the leaf control system have a brain, okay, which we call it signal processing, okay, and one of the brain normally used is PLC, okay, which is the Programmable Logic Controller. So the leaf will then move to level 4 because it knows that someone has requested for a leaf at level 4. Okay, so how does the leaf move? Okay, the leaf move using motors driven by motor driver card, motor contactor, or even motor relays. Okay, so you can see how the leaf control system has these 4 components of the control chain. And there are many different examples that we can actually apply using this control chain, which I will go through with you in the next few pages. Page 2 of the worksheet. Okay, the next example I want to talk about is automatic warehouse door control system. So for this automatic warehouse door control system, it has ultrasonic sensor and a photoelectric sensor to sense whether the vehicle is approaching and whether the vehicle has passed through the door. And there's a controller that takes in all the signal and drive the motor to open or close the door. So how do we fill in this example? Okay, so you can see this automatic warehouse door control system. The input elements will definitely be the sensors, okay, because only with the help of the sensor, you can decide whether to open or close the door. So the ultrasonic sensor and the photoelectric sensor, okay, is the input element of this control system. So the brain of this system will definitely be the controller because it will drive the motor. So the motor is actually the output element because it drives the motor to open or close the door. Okay, and the final control element will be the motor contactor. Okay, because you can read this statement, a controller take in all the signal and drive the motor to open or close the door via the motor contactor. So the motor contactor is the final control element. Okay, so let's take a look at the second example. This greenhouse temperature control system. So in this greenhouse temperature control system, there's a computer that will continuously read the temperature of the greenhouse through a temperature sensor, and then it will then regulate the temperature within 26 to 28 or 24 degrees, plus minus 2 degrees. Okay, so if the temperature is too high, the window panel, you can see at the diagram figure 2.2, the window panel will be opened using a pneumatic cylinder. So you can see the cylinder is here. Okay, so if the temperature is too high, the cylinder will extend. If the temperature is too low, okay, the panel will be closed, so the cylinder will then retract. So how do we fill in the blanks for this? So the input element for this greenhouse temperature control system is definitely the sensor, okay, the temperature sensor, because the temperature sensor will sense the temperature of the greenhouse. And then the computer is then the brain to decide whether to open or close the window panel using a pneumatic cylinder, which is the air cylinder. And how does it know whether to extend or retract? Okay, the computer will decide, but to make the cylinder extend or retract, it actually has something called a directional control valve, which I will teach you later on how does a directional control valve works. Okay, so the directional control valve is the final control element. Okay, next, let's go to the next page, page 3, traffic light control system. This is a simplified traffic light control system which is driven by a programmable controller. So the green light is normally turned on until some pedestrian activate a push button at the traffic light control panel. Okay, and then you can read that when this happens, the traffic light will turn red, green man will turn on, and they ask us to complete the following control chain for the control of this AC powered green man light. Okay, so you can see that over here, this is a simplified traffic light control system which does not need a final control element. So what is the input element for this traffic light control system? It is the push button, okay? Because only when the pedestrian activate the push button, then the brain will start to think, okay, which the brain will be the programmable controller. Okay. Then once it thinks that, okay, it's ready for the green man to turn on, or called the green man light, then it will turn on the green man light, which is the output element. Because this is the outcome of this traffic light control system, which is to turn on the green man light. Now we are at page 4 of your notes, EP1. So in this page, we actually compare the technologies for implementing power section. We have the pneumatic technology, hydraulics, and electrical technology. So this page actually lists out the pros and cons of each technology. I will leave you all to read this page by yourself. So if you have any questions, please feel free to go back to your lecturers and post your questions to them. So next, I will go through the last example of EP1, which is the cash card machine. So you may want to read this cash card machine problem statement. In figure 3a, there's this cash card machine using a controller to process all the transaction, okay? So the machine comprises of the following features: a read head, a sensor S1, a barcode scanner, a accept push button, a write head, a 4-digit display, and a rate indicator light. Okay, so we are supposed to fill in the blanks over here. Perhaps let's try to fill in the blanks for input element. So I can see that for this cash card machine, I definitely need the read head because I need to read the store value of the cash card before I decide to do anything, right? So the input element will be the read head. I also need the sensor S1, okay, as you can see over here. And I will also need to have the barcode scanner because I need to read the sales price. If I don't read the sales price, I do not know what to do to this cash card. So the barcode scanner, okay, and I will also need a accept push button so that for the customer to confirm the sales. So only when you press this button, then this cash card machine will proceed to do something to the cash card, right? So the next one will be the accept push button. Okay, is there any more input element? From here, I don't think so. Okay, next, let's look at what is the signal processing element. Okay, what is the brain of this system? Okay, you can see that the brain of this system is the controller, okay? And what is the outcome? Okay, what do you expect this cash card machine to achieve? Okay, first, it will definitely need a write head because only by reading what is your cash card value, knowing how much to deduct, I need to use the write head to deduct, okay, or to write in the balance value. So the write head is definitely the output element. And also the 4-digit display because you need to display to the customer, okay, this is the sales price as well as the original store and balance value of the cash card. So the 4-digit display is the output. And finally, if the transaction are not approved, the rate indicator light will be on. So the rate indicator light will be the outcome as well, which is the output element. Okay. Oops. Okay, rate indicator light. Okay, so let's check whether we have filled in all the things in here. Rate indicator light, 4-digit display, write head, accept push button, scanner, read head, S1 controller. Okay, we are done for this question. Now we look at worksheet 2, where worksheet 2 will introduce you output element and final control element. And if you still remember from worksheet 1, in a control chain, is made up of input element, signal processing element, final control element, and output element. So in this worksheet, we will first talk about output elements, which are components that produce motion, okay, or torque or force. So we will introduce to you pneumatic cylinder first. And what is the range of pneumatic air pressure that we normally use for all these pneumatic components? Okay, it's normally 6 bars. Okay, which is around 6 times 10 to the power of 5 Pascal. Okay, now I'm going to show you how a pneumatic cylinder looks like. Over here, you can see that this is one of the cylinder you can find in our lab. Okay, this is the ball side of the cylinder, and this is the rod side of the cylinder, as you can see. Okay, so these are the air port. Okay, so over here in the air port, you'll plug in the pneumatic air tubing. Okay, and over here, you can also plug in the pneumatic air tubing for the rod side of the cylinder. Okay, so where are these tubings going to be connected to? Later on, you will know that they will be connected to the directional control valve, whereby your directional control valve will be connected to the air manifold, or we call it the air supply, so that the cylinder, when there's air coming in from the ball side, which is here, it will extend. Okay, you can actually see extend. Okay, however, when there's air coming in from here, the rod side, you can see that the cylinder will retract. Okay, so
Think about this. What type of cylinder is this?
There are two types of pneumatic air cylinders. Okay, one is a single acting cylinder, another one is the double acting cylinder. What does it mean by single acting cylinder? Okay, single acting cylinder means that there's only one air port and there is also a spring inside the cylinder. Okay, so let's take a look at this example, normally retracted type. Okay, so for normally retracted type single acting cylinder, again, as I mentioned, because it's a single acting cylinder, it means that there's only one air port, which means that it only allows air to go in via this air port or come out from this air port. Okay, and the other side is the spring. Okay, so let's take a look at this. If air goes in from this air port, the cylinder will extend. However, if there's no air coming in from this air port, the spring over here will cause the cylinder to retract and the air will come out from here. Okay, so that's why default is a normally retracted type cylinder. Okay, so let me draw this out for you. This is the symbol for a single acting normally retracted cylinder. There's only one air port. I call it port A. Okay, and this is the spring. Okay, this one is a normally retracted cylinder. Okay, next, how do I draw a normally extended single acting cylinder? Okay, this is how you draw. Because it's normally extended, right, means that the spring must be on the left. Okay, this is the spring. And this is the air port. So this is a normally extended single acting cylinder. Okay, next, let's go through this double acting cylinder. So what does this mean by double acting? Double acting means that there are two air ports. Okay, so there's no spring. I label it port A, port B. So how does this cylinder extend? Okay, so when air goes in from port A, it will extend and the air will come out from port B. So as long as the air is continuously pumping from port A, the cylinder will stay extended. But how does the cylinder retract? Okay, so the cylinder will retract if, again, I label this port A, port B. So if air goes in from port B, it will retract, okay, and then the air will come out from port A. So how do I draw this cylinder? Okay, to draw this cylinder is very simple. Okay, so if you want to draw the retracted position, it's just this. No spring inside, only two air ports. Okay. And if you want to draw it as extended, again, this is how you draw, and label port A, port B. Okay, maybe I should write clearly. Okay, so this is double acting cylinder. So to control this movement of the piston rod, right, what should be the final control element that can direct the flow of the air into the cylinder to cause it to extend or retract? Because we know that if air goes in from left to right, coming out, it will extend. If air goes in from right and comes out from the left, it will retract. So the component that can be used to actually automatically switch the flow of air into this cylinder is called a directional control valve. So in the next page, I will first teach you how to name the various type of directional control valve. Let's start off the naming process by first knowing some of the symbols that you must know. Okay, so this symbol is actually exhaust, okay, which means air coming out. This symbol means supply, air supply, which means air going in. Okay, this one means the number of switching boxes. In this case, you can see very clearly that there are 2 switching boxes. Okay, this one shows the control connections as shown by the lines drawn on the outside of the box. So how many control connections are there? Okay, you can see 1, 2, 3, 4. So there are 4. So again, likewise the same for this 1, 2, 3, 4. So this one is, it means the control number of control connections. Okay, so take a look at this. How many switching boxes are there? 3. Okay, and this one means the flow path. Okay, the arrow shows the direction of the flow. This one means shut off position. Okay, and we will learn how to name this directional control valve now by knowing all this terminology. Okay, first of all, to start off naming this directional control valve, the first step is we always like to say x/y way, okay, where x is the number of controlled connections, okay, and y is the number of switching boxes. Okay, so let's take a look at this directional control valve. Okay, look at this directional control valve. How many way is this? Okay, x is the number of controlled connections. So let's look at this. I shall expand this diagram slightly. Okay, let's focus on only one box. Okay, how many control connections are there? 1, 2, 3. So it's a 3 slash. Okay, and how many switching boxes are there? 2. Okay, so it's a 3/2 way. Okay, let's look at the next example. How many control connections are there? Okay, you can focus on the box on the left or on the right. Okay, so this time around I look at on the left. Okay, the control connections are 1, 2, 3, 4. So it's a 4/ and there are 2 switching boxes, 2 way. Next, let's look at the other one. This one will be a 5/2 way. If you still do not know why, let's look at one of the box. Okay, in this box, how many controlled connections are there? 1, 2, 3, 4, 5. That's why it's 5. And there are 2 switching boxes. That's why it's called 5/2 way. Okay. So we are done with the first step. Let's look at the second step. Second step is to recognize whether it's a single or double solenoid. Okay. Okay. Again, let's look at the examples below. Look at this example first. Okay, there is only one solenoid. This is a solenoid. Okay. This one is a spring. So this one I will call it 3-2-way single solenoid. Okay, and how do I know whether it's a double solenoid? Let me give you another example. Maybe let's look at this example, the one beside it. Okay, so for this example, this one is also a 3-2-way, as you can see, but it's a double solenoid because it has two solenoid. Okay, so for this, I will just write here 3-2-way double solenoid. Okay, so this is how you can easily recognize whether it's a single solenoid or a double solenoid. Okay, finally, what is the third step you need to know? Okay, the third step you will need to know is this. Okay, to be able to know whether it is a normally open, which we call it NO, okay, stands for normally open, or normally closed. Okay, what does it mean by normally open, normally closed? Okay, when we say that it's normally open, it means that the air can pass through the directional control valve. Okay, when we say that it's normally closed, it means that the air is blocked by the directional control valve. Okay, now let's take a look at this example over here. Okay, this one I will say that is a 3-2-way because if I look at one box itself, there are 3 controlled connections. So this one I know is a 3/2-way, and I know it's a single solenoid, okay, which is recognized by this. Okay, and is it normally open or normally closed? Okay, to know, let's look at the air. This is the air supply, right? So you know that this is the air, and is it blocked by the directional control valve? Yes, it is. Look, this is the air. It's being blocked by this directional control valve. So I will call it is a normally closed directional control valve. Let's take a look at the next one. Okay. Again, I know this is a 3-2-way, also a single solenoid, which is recognized by this. So I call this 3-2-way single solenoid, and I know that it is normally open because if you look at the air supply, this is the air supply, okay? It can go through the directional control valve, right? So it's a normally open directional control valve. Okay, so with this, you can actually scroll down and try to fill in all these examples yourself. Okay, like for instance this, can I actually name it properly since I already know that it's a 5-2-way? Okay, so This one is a 5-2-way double solenoid, normally open directional control valve. It's normally open because look at this, this is the air and it can go through the directional control valve. Okay, the same thing on this DCV, except that is a single solenoid, normally opened directional control valve. Okay, again, why normally open? Because the air is here and it can go through the directional control valve. Okay. Okay, we will leave the rest for you to fill in yourself, and if you have any questions that you're not sure, please feel free to ask your lecturer. If not, we will move on to the next page, which is how this directional control valve actually works. Okay, how does it do the auto switching to make the cylinder extend or retract?
Now I'm going to show you the double acting cylinder, okay, and how I'm going to use the directional control valve, 4-2-way double solenoid directional control valve, to control the extension and retraction of this cylinder automatically. So first, I will draw the solenoid on this directional control valve. Solenoid 1, SOL1, and solenoid 2, okay. Next, I will draw the air supply that's being connected to this DCV and the exhaust as well. Okay, and this cylinder is being connected to this DCV using pneumatic air tubings. So one side to the ball side of the cylinder and the other side to the rod side of the cylinder. Okay, so now when I energize solenoid 2, you will activate this checkbox because this checkbox is closest to solenoid 2. So the air from the air supply will pass through this DCV and go to the rod side of the cylinder, causing the cylinder to retract, and the air will then come out from here to the exhaust of the DCV. Okay, next, to make it extend, I will first need to de-energize solenoid 2, okay, and energize solenoid 1. So this DCV will switch, okay, because you will activate this box, because this box is closest to solenoid 1 and you have energized solenoid 1. So it will switch to here, and you can visualize that the air supply will pump in the air to the ball side of the cylinder, making the cylinder extend, okay, and the air will then come out from the rod side to the exhaust. So how do I make the cylinder retract again? First, you have to de-energize solenoid 1, okay, and energize solenoid 2. When you energize solenoid 2, you will activate this checkbox because this checkbox is closest to solenoid 2, and you can see that the air supply will pump in the air to the DCV to the rod side of the cylinder, causing it to retract, okay, and the air will come out from here to the exhaust. So this is how the DCV can be able to use to connect to the cylinder to control the extension and retraction of this cylinder. And that's why DCV is a final control element and cylinder is an output element.
Just now you have watched how we actually can connect a 4-2-way double solenoid DCV to a double acting cylinder. So now we are just going to go through this concept again on the worksheets. So let's take a look. I'm going to draw the double acting cylinder, and double acting cylinder has two air ports, A and B. I'll just label them for clarity, and it's being connected to the DCV via pneumatic air tubings. Okay, I will also label the solenoid of this 4-2-way double solenoid directional control valve, solenoid 1 and solenoid 2. So for this example, you can see that solenoid 2 is being energized, so it will activate this checkbox here. So the air supply will pump in the air through the DCB to port B, okay, causing the cylinder to retract, and the air will come out from the ball side through port A to the exhaust. Okay, so what happens when you energize solenoid 1? So when you energize solenoid 1, let's look at this diagram now. When you energize solenoid 1, okay, again, let me draw the double acting cylinder again. Okay, it's been connected like that. Okay, so when you energize solenoid 1, you will activate this check box, okay, because this check box is closest to solenoid 1. So the air will pump in from the air supply through port A, okay, causing the cylinder to extend, okay, in this case, and the air will come out from port B and then later on go to exhaust. So this is how it works. Let's go through another example. So now, what if I crisscross the tubing? Okay, what do I mean by that? Okay, first of all, let me draw this cylinder air port connected to the DCB this way. Can you see that the tubings are now being crisscrossed? Okay, so let's take a look. When you energize this solenoid, okay, I will also label this solenoid 1, solenoid 2. So when I energize solenoid 2, you activate this checkbox, and can you see the air supply is here? You go to here, and because the tubing is now crossed, you will actually go to port A. Okay, so the cylinder will be extended, and the air will then come out through port B to the exhaust. Okay, so what if now I'm going to energize solenoid 1? So let's look at this diagram now. This diagram. Okay, what if now instead of solenoid 2 I energize solenoid 1? Okay, the tubing again was crisscrossed, so it will remain crisscrossed. Okay, and port AB. So let's visualize now. So the air supply is here. Okay, it will go through the DCB to port B, okay, and then because it goes through port B, you'll push the cylinder and make it retract. So I'll draw the cylinder being retracted, okay, and the air will come out via port A going to the exhaust. So this is how a 4-2-way double solenoid DCB can control a double acting cylinder, extend and retract. Okay, so this is some of the examples of application for double acting cylinder. You can use it to lift and lower workpiece between two levels. So you can see this cylinder over here. You can extend to raise this, and you can also retract. Okay, next, look at this example over here. This is a clamping of a workpiece in the bending operation. So you can actually use the double acting cylinder as a clamping cylinder, okay, to actually bend this workpiece. Okay, you can see that there are two cylinders over here. Now we will go through the single acting cylinder and how we actually connect the DCB to the single acting cylinder. Okay, first, what do we mean by single acting cylinder? As you know, in previous pages, right, we said that single acting cylinder means that there's only one air port. Okay, so this is the air port, and this is a normally retracted cylinder. Okay, okay, so now let's take a look at this example whereby we are using 3 two-way valve to control this single acting cylinder. So as you can see, before I do anything, I would like to label the solenoid first. So in this example, we are energizing solenoid 2, okay, because there's only one connection on the DCB, so the air port will definitely be connected to this connection on the DCB. So as you can see, the air will definitely flow to the exhaust. Okay, this is the exhaust symbol, the triangle. Okay, so since it's going to flow to exhaust through the ball side, definitely the cylinder will be retracted. And there's a spring here. Okay, so let me go through this again. Can you visualize that the air from the ball side will be going into the DCV to the exhaust? Okay, that's why the cylinder is normally retracted. Okay, now let's look at this example. Okay, over here, again using a 3-2-way valve, I will label this solenoid 1 and solenoid 2. Now instead of energizing solenoid 2, we are going to energize solenoid 1. And because there's only one connection, right? Okay, so definitely it's going to be connected like that from the cylinder to the DCV. So as you can see, this is the air supply. So the air will flow through the DCV into the ball side of the cylinder, hence causing it to extend. Okay, it will extend. And you can see the spring here is being squashed, okay, compressed. So the cylinder has extended in this case when solenoid 1 is being activated. Okay, now let's take a look at this. Can I actually use a 4-2-way and replace it instead of using a 3-2-way valve? You can see over here, this is a single acting cylinder. There's only one air port. However, on the DCV, there are 2 connections. So what can I do about this? Well, you can still use a 4-2-way valve to connect, okay? However, you need something called a stopper. Okay, so I will connect a stopper over here. The rest will be just like how I connect using a 3-2-way. Okay, and again, this cylinder will be retracted. Okay, because the air is coming up from the ball side into the exhaust. Okay, so same thing over here. Okay, look at this diagram. The stopper is still attached to this connection over here, and the air tubing is being connected between the cylinder and the DCV. And when you energize this solenoid, you activate this box, so the air will actually flow from the air supply through the DCV into the ball side, causing the cylinder to extend. Okay, and the spring is being compressed. So I would like to go through this again. What is this called? This is a stopper. Okay, it's just like an air stopper. And you can see from this example that single acting cylinder, you can use a 4-2-way valve to control it. Even though there are 2 control connections on the 4-2-way valve, you can just block one of them with a stopper. And if not, you can just use a 3-2-way valve to control a single acting cylinder. So what are the applications of single acting cylinder? Okay, things like pressing of a bolt into a workpiece. Okay, like for instance, you only need to work in one direction only, which is the air supply direction. You can actually have this cylinder to push the bolt into the workpiece. Okay, same thing for this, ejecting a workpiece into a carrier boat. Okay, you just need to have it work in one direction as well, which is the air supply direction. So you can actually make it extend and it will push the workpiece into the carrier boat. Okay, that's all for directional control valve. I hope you understand how directional control valve works and how you can actually apply them to control double acting cylinder or single acting cylinder.